Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will extend my discussion on the course of linear algebra, and the topic which I will cover in this lecture is properties of eigenvalues and eigenvectors. So, whenever we have a diagonal matrix like this, then the eigenvalues of this matrix will lie on the principal diagonal. So this is called the principal diagonal or main diagonal. So for this matrix, the eigenvalues are lambda 1 equal to 3 and lambda 2 is equal to 2. We can prove this thing. So eigenvalues are the diagonal entries. Let's evaluate the eigenvalues of this matrix. So lambda I minus a determinant should be equal to 0, and this is lambda I matrix, this is A matrix. We can subtract them and we can take the determinant, and their determinant is equal to lambda minus 3 into lambda minus 2. So by equating this determinant to 0, the roots can be evaluated, and the roots are lambda equal to 3 and lambda equal to 2, and these are the diagonal entries. So in the straightforward way, we can write that these are the two eigenvalues of the A matrix. Now let's evaluate the eigenvectors of this diagonal matrix. For evaluating the eigenvectors, we have to use this equation Ax is equal to lambda 1x. This will give us the first eigenvector, and Ax equal to lambda 2x will give us the second eigenvector. So let's uh, convert this matrix to the equation form, and this is A matrix, this is x column vector, x1, x2 is equal to lambda 1 and 2x, and we can expand these two equations. So 3x1 equal to 3x1. This is the first equation, and we can assume that x1 is equal to 1. So it is best to assume the smallest and simplest value whenever we have such an equation. So this equation will be satisfied on all the values of x. So we can assume x1 equal to 2, we can assume x1 equal to minus 2, and so on. But it is the best practice to assume the value of x1, which is the smallest and simplest, and that value is 1. So let's assume that x1 is equal to 1. Now let's expand the second equation, and it will be 2x2 equal to 3x2. Now in this equation, the only condition which can satisfy this equation is x2 equal to 0. For any other non-zero value of x2, this equation will not be satisfied. So we can say that x2 is equal to 0 in this case. So the first eigenvector will be equal to x1, x2, and x1 is equal to 1 and x2 is equal to 0. So our first eigenvector is 1, 0. Now let's evaluate the second eigenvector, and we have to write Ax equal to lambda 2x. Let's write this equation in the matrix form, and then we can establish two equations. First equation is 3x1 equal to 2x1, so x1 equal to 0, and 2x2 equal to 2x2. So again, in this case, x2 will be equal to 1. So the second eigenvector will be x1, x2, which is equal to 0, 1. And we can establish the matrix of two eigenvectors. First eigenvector is 1, 0, second eigenvector is 0, 1. So the matrix of eigenvectors is expressed as y. So y equal to x, x dash. So that will be equal to 1, 0, 0, 1. So we can observe that if we have a diagonal matrix, the eigenvalues are the diagonal entries of that matrix, and the matrix of eigenvectors is an identity matrix. So this is the first property of eigenvalues and eigenvectors for a diagonal matrix. So the eigenvectors of a diagonal matrix constitute an identity matrix. So let's solve another example. And in this example, we have an upper triangular matrix. So for an upper triangular matrix, the eigenvalues are the main diagonal when a matrix is a triangular. So if we have such a triangular matrix, the eigenvalues are the values at the main diagonal. We can also prove this by evaluating the eigenvalues of this matrix, and lambda I minus a determinant should be equal to 0. And by equating this determinant to 0, we will get at the end lambda minus 1 into lambda minus 3 by 4 into lambda minus 1 by 2. So you can evaluate the determinant of this triangular matrix, and that will be equal to this equation. And the roots of this equation are lambda equal to 1, lambda equal to 3 by 4, and lambda equal to 1 by 2. So these are the three eigenvalues, and we can see these are the diagonal entries. So for a triangular matrix, either it is an upper triangular matrix or it is a lower triangular matrix, the eigenvalues will be the diagonal entries. So this was the second property. Another property is that sum of n eigenvalues equals the sum of n diagonal entries, and product of n eigenvalues equals the determinant of A. So these are also two important properties of eigenvalues. So for any matrix, either it is a triangular matrix, diagonal matrix, or it is a full matrix, the sum of n eigenvalues will always be equal to the sum of n diagonal entries, and the product of n eigenvalues is always equal to the determinant of that matrix. We can prove this property. So we know that trace of any matrix is equal to the sum of the diagonal entries. So if we have an n by n matrix, which is the A matrix, and the trace of that matrix A will be equal to the diagonal entries A11 plus A12 plus so on up to A, and sum of all diagonal entries is equal to the trace of that matrix. And suppose we have such a matrix A equal to A, B, C, D. The trace of this matrix is equal to A plus B, and the determinant of this matrix is equal to AD minus BC. So let's evaluate the eigenvalues of this matrix. So lambda I minus A determinant should be equal to 0. And this is lambda I minus A. By evaluating its determinant, we will get this quadratic equation. And this quadratic equation can be written as lambda square minus A plus D is equal to the trace multiplied by lambda plus this term is equal to the determinant. So this is determinant of A. Now the roots of this quadratic equation are equal to trace, right? Minus B plus minus B square minus 4AC under root divided by 2A. So this is trace plus minus trace square minus 4 times determinant divided by 2. So these are the two eigenvalues. So lambda 1 is the eigenvalue with positive sign in between, and lambda 2 is the second eigenvalue with negative sign in between. So lambda 1 plus lambda 2 will be equal to trace, right? So plus and minus will be cancelled out, uh, and we will have trace by 2 plus trace by 2. So lambda 1 plus lambda 2 is equal to trace. Similarly, lambda 1 multiplied by lambda 2, product of the two eigenvalues will be equal to this eigenvalue multiplied by this eigenvalue. So after multiplying these two eigenvalues, we will get 1 by 4 into trace square minus the under roots will be cancelled out. So we will have trace square minus 4 times determinant. So trace square minus trace square will be cancelled out, and we will have 1 by 4. This minus minus will be equal to plus 4 times determinant. And at the end, we will have the product of two eigenvalues equal to the determinant. So these two properties have been proved, right? So the sum of two eigenvalues is equal to the trace of the matrix, which is equal to the sum of diagonal entries, right? And the product of two eigenvalues is equal to the determinant of that matrix. So another property is that whenever we have a singular matrix, it's at least one eigenvalue will be equal to 0. So from this second property, product of n eigenvalues equals the determinant of A. So according to this property, if we have a singular matrix, the determinant will be equal to 0. And in that case, if we are evaluating the eigenvalues of that singular matrix, there will be at least one eigenvalue which is equal to 0. So that the product of all eigenvalues will be equal to 0. So that product can be equal to 0 if and only if there is at least one eigenvalue equal to 0. So that is all about some important properties of eigenvalues and eigenvectors, and I hope you have enjoyed the contents of this lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.